Hi kids, Mr. Josephs here. I'm going to talk to you today about the history of the atom, and more specifically, the structure of an atom. And what is an atom made of? We know that atoms make up everything around us. They make molecules and all sorts of substances. But an atom itself is actually made up of smaller particles. We call them subatomic particles. And we will look at what those are. But first we're going to step back 2,000 years ago, 2,500 years ago, to a guy named Democritus. And he was a Greek dude, and he theorized that matter was made up of particles. Before that, most people thought that matter was what we call continuous. That means you could divide matter up. Let's have a piece of matter, and we divide it up. We take a piece of it, and now it's smaller. And then you could slice that again, and that's smaller, right? And then you could slice that piece again, and that's tinier. And you could do this forever. Slice it forever. And Democritus said, that's silly. Eventually you get to a piece that's the tiniest piece of matter, and he called that an atomos. And that's where we get the word atom from. And he said, after that, you can't divide that any smaller. That's the smallest piece of matter. The funny thing is, he had no way of... Oh, peace. Come on, Mr. Josephs. He had no way of proving it because science hadn't been invented yet. And so there was no scientific way or experimental way to show that matter was made of a tiny little piece. It's funny, though. He turned out to be correct. Now, later on, in the 1700s, came along a guy. He was an English teacher, I think, or he was a teacher. I know that. And his name was John Dalton. And he did some experimentation. I really don't know what his experiments were. I think he was doing experiments with burning substances in oxygen and seeing how oxygen atoms attached to the objects that he was burning. But he came up with 4 postulates what an atom is like. And so he said that all elements are composed of indivisible atoms. And we know from the last unit that elements are made of one type of atom, right? So that's basically what he's saying here. Well, that's not necessarily true. He's just saying that they're made of atoms that are indivisible. His second postulate is that all atoms of a given element are identical okay. So the first one says they're indivisible atoms. They are the smallest particle that exists. The second one says that the elements of a given atom are identical. That means if you found an atom of oxygen in nature, and then you went to the other side of the world and you found an oxygen atom over there, they are exactly the same. No difference whatsoever. Turns out that there can be some differences of within a particular type of atom, but we'll talk about that at some other point. They're called isotopes. If you watch some of other of my videos before this one, you might have seen what that means. Atoms of different elements are different. That's kind of funny how he says that. Atoms of different elements are different because they have different masses. So he said an oxygen atom is different from carbon atom because it has a different mass. Now, the way we identify differences in atoms is not by the mass today. It's by something else. It's by the number of protons that are in the nucleus. But he didn't know about nucleus in an atom because, remember, number one here, he thought that they were indivisible. So he just thought they were one particle made of one thing. Okay? He didn't think they were made of anything else. Okay? But some of his postulates here are useful for our purposes today, especially this last one, which he said compounds are formed by the combination of atoms of different elements. And they are made, and we know this already, right? So, for example, like water, it's made up of an oxygen and 2 hydrogen atoms. That's a compound of water, these different elements combined in specific ratios. It has to be in a specific ratio because they're in a chunk, they're in a molecule. So, and that's really what we want to know about chemistry. Anything we do in chemistry is we want to understand how these elements, these atoms of elements, stick together. And by stick together, I mean bond chemically together to form substances with properties that we want. As humans make substances for our own purposes so that we can do things with them. Like make Gorilla Glass for like an iPad or something like that. Like it's a really strong material that's clear and can be used in an electronic component. We had to know how to put things together in order to do that. That's the whole purpose of our chemistry. How do these things get together? How do we put them in certain formations? Well, it's really important that we understand how an atom, the structure of an atom is, because that will tell us how they actually stick together. Now, Dalton, if you look here, Dalton doesn't have any explanation of how to stick atoms together. He just says that they do form compounds, but he doesn't tell us how. Now we're going to get into some understanding of the structure of an atom that will give us some understanding of how they stick together. Okay? I'm not going to tell you how they're going to stick together in this video, but you really need to understand how the structure of the atom exists in order for us to start to talk about that. So, the next one, we come across J Thompson. I'm not really sure when he was. Let me look that up for you. J Thompson. I think he was in the early, I think he's like 1903 or something like that. Let's see. 1897. So, J Thompson. 1897 experiment. What was his experiment? His experiment was something called a cathode ray tube. He took two charged plates, basically like a magnet. One was negative and one was positive. And he had this big old cathode ray tube. It's really a weird thing. Okay, I'm going to draw a really stupid picture of it. He had some material, some matter, that he stuck into it, okay? This matter right here. Well, this matter is neutral. All right? That means it doesn't have any charge. And he had a screen over here that he had. Oops, that's not what I want. He had a screen over here. This is what we call a phosphorescent screen. And out of this cathode ray tube, these little particles started coming out. All right? He shot these particles. They came from the neutral material. But these particles, they actually went up. How do you know they went up? Because they're invisible. You know they went up because when they hit the screen, they made this little pinprick of light, like this little flash of light. And all the flash of light was all up on the top part of this screen. So he knew that the particles were moving upward, or they were deflecting sideways up toward the positive charge. What does that tell you about this right here? This stream means that this stream of particles, these particles are negative because opposite charges attract. All right? Now, if the particles are negative and they're coming out of a neutral substance, something else had to be left behind. What's left behind? Left behind are positive things. They have to be positive things because if negatives came out and the original stuff was neutral, that means that there has to be some positive in there too to balance out the negative. And so his view of the model becomes something that was different from Dalton. Dalton just said that the particles were indivisible, okay? But he came up with this model, which we call the plum pudding model. So if we look at an atom, the atom has just some positive, it's a big positive sphere, okay? And then he said stuck in this positive sphere are negative things. That's the stuff that was streaming out of the cathode ray tube, and then the positives would be left behind. Now, the negatives have to equal the positives, so we have to make sure that we have these little particles equal in number to the charge that's on the big one. We call this the plum pudding model because British people eat weird stuff. They have this plum pudding. I guess the negative things are the plums in the pudding. I've heard it also said that they were actually raisins in the plum pudding. So it's like raisins in the plum pudding. The positive stuff must have been made out of the plum stuff. I really don't know. That sounds disgusting to me. But that's the plum pudding model for J Thompson. All right. So after the plum pudding model, we have another really famous experiment. This is by a guy named Ernest Rutherford. And I don't know how these guys come up with these weird experiments, but they do it. And in 1911, he had this big block of lead. Okay, I'm going to get my draw on here. And inside that block of lead there was a hole, and we'll show this as a cutaway. And inside that hole was this radioactive stuff. So he had some radioactive stuff in that hole. Okay, and that radioactive stuff, radioactive stuff. I'm going to just call it stuff. All right. Now that radioactive stuff causes some things to stream out, and these things that stream out of here, okay, are called alpha particles. And these alpha particles are positive. So positive alpha particles. And guess what he shot this stuff at? He put in the way Oops, I did that again. Oh, I'm so smart. Yup. He put in this way some gold foil, only a couple atoms thick. Yeah, I don't know how he did it. Let's make this little golden color. Ooh, look at that. So this is gold. Oh, gold foil. And he also had a screen behind it, kind of like what J Thompson did. He had a screen that was went around the gold foil. Okay. Oh, that's a terrible drawing. Oh, I put that on the wrong side. Okay, so it came down like this, and it went around like that. So you can see this, and it actually went. Let me reduce the size of this gold foil because it actually was a little smaller. So it would be like this right here, and the screen came. Oh man, come on! The screen came around like this. Okay, and the alpha particles. I keep using the wrong pen. All right, the alpha particles went streaming through here. Okay, let me make them a little more like the particles. They went streaming through here, and when they got to the gold foil, he thought, based on the plum pudding model, that they'd all just go through and hit the back, and there would be little pinpricks of light when the particles hit there. Okay? What he found was most of them did go through there and hit the back, but some of them deflected and went over to the side, and then they would make little pinpricks of light on the screen. And once in a very long while, some would come back like this. And he said it was like a bullet from a gun hitting tissue paper and coming backward. And he's like, what the heck is going on? How do what does an atom look like then? Right? So this gold foil, it must have something in it that's causing these alpha particles to bounce back. What in the heck could it be? And so now, what we get is something called the nuclear view of the atom, which just means that he said that the atom must have a nucleus. So remember, in J Thompson's model, all that positive was spread around the atom. He says now, guess what? All that positive stuff is in the center. So I'm just going to put all that positive stuff in the center. All right, and the negative things are still outside like this. Oh, that's interesting. Okay. So he's saying that this whole thing is the atom, right? And they're just kind of sitting in there like this. Okay, this is the atom. And those alpha particles, those positive alpha particles, when they came streaming through, here we go, alpha particle, alpha particle, alpha particle. Because these are positive, he knew they were positive because they would be attracted to a negative plate. They would pass through most of the atom because there was empty space. Sometimes they'd get close to the nucleus, this positive nucleus, and they'd get pushed off to the side because two positives will detract from each other, or repel from each other. And then sometimes there's a direct hit on the nucleus and it would bounce backward. That's what he said. He's like, that's what it must look like then. And so he came up with two important postulates or two important theories about the atom that you really have to know about. One, because the atom is made of mostly empty space. In fact, he said it's 99% empty space. There's nothing in the atom. Okay? Why? You have to have a reason for why. Because most of the alpha particles passed right through. Right? So if they pass through, it must be empty space. His second thing was, he said, there's a nucleus. So the positive charge is concentrated in a nucleus. That's a terrible spelling, Mr. Josephs. In the nucleus, the positive charge is concentrated in a nucleus at the center of the atom. How come? Well, he said, because, and it's very, very tiny little center, and that's because some some alpha particles bounce back, or they were deflected off to the side. Okay, so those are the two things you really got to know about Mr. Rutherford's view of the atom. And then Niels Bohr came along in the 1920s. It's so funny, I'm like, my grandfather was born in 1920. He just died a couple of years ago, but I still think it's amazing that this guy was alive doing his experiments at that time. There's no specific experiment that we're going to talk about for him, but he discovered that these we've got the positive in the center still, and I'm going to actually call them put them as protons, and the number of protons tells you what type of atom you have. Unlike Dalton, who said you know what the atoms are because they have different masses. It's really because they have different numbers of protons. It took a while to actually realize that. There's also some neutrons in the nucleus. Those just add mass to an atom. They're not very important for this particular reason, or for this particular part. Okay, and Niels Bohr said that the electrons are in specific rings or energy levels around the nucleus. So I'm going to label these electrons now as little E minuses. That's a very standard way to do that. And we'll put them in this little ring. So then the first one, there's 2. And we need to have 5 electrons because there's 5 protons in the center. We did not need to put 5 neutrons. I did that just because it's common to have the same number, but it's not always the case. That's how we have different versions of the same atom. You know, I really should just have that memorized, but I'm pretty sure this is a atom of boron. Look at the reference tables, number 5. I'm really tired. Yeah, it's got to be boron, right? Let's see. Sure is boron. Right. Because of 5 protons in the nucleus. So Niels Bohr said that you have these energy levels, and electrons can bounce up to higher to energy levels if they're given energy, and when they bounce back, they're going to give off light. It's really cool. We're going to do a lab that deals with that kind of stuff. It's pretty awesome. And yeah, that's that. Okay, the final guy, and this is actually a bunch of different people actually, but we can name him this Werner Heisenberg. He has the Heisenberg uncertainty principle. He says that you can tell where an object is, or you can tell how fast it's moving. You can't tell both. So he still has a positive nucleus because that's what it is. We really know that. But these electrons now are in certain orbitals, and it's called the electron cloud model. And you can't really tell where the electrons are. You can tell, if you do tell where the electrons are, electron is, then you can't tell other information about it. You really don't have to know a lot about this, other than that it's called the electron cloud model in the Regents, and this just tells you you can't know. So electrons are located in orbitals, and it's uncertain as to where they are. And that's about it. So that's the history of the atom. The one that we use the most is going to be the Bohr atom. It's still very useful for us to visualize the atom in this way, especially at the level of chemistry that you're going to be learning. And this model right here is going to help us to understand how we can get another atom attached to another atom. Okay, so we want to take atoms and we want to form new substances by attaching them together. And they have this structure that help us to understand how they can attach. And we'll be discovering that in the future. And that's the most exciting part about this stuff, is that we can attach other atoms to others in a chemical bond and make new and useful products for us humans to use. All right? Okay, so that's about it. Have a great day.